Welcome to the course A Journey Through Genius. In this course, we are going to look at the aesthetic side of mathematics. So, we are going to visit mathematical theorems and ideas that are beautiful, that have some aesthetic quality. And we would like to learn how to appreciate mathematics the way a mathematician does, purely for its aesthetic reasons. It is very sad that people feel very embarrassed if they can't quote Shakespeare or if they cannot say something meaningful about a painting of Van Gogh, whereas many people take pride in not knowing a single mathematical theorem or a proof. This course is an attempt to change that. Today we are going to look at three beautiful pieces of mathematics. They're very simple, but we are going to see the aesthetic side of these pieces, and we're going to see how the solution, how they solve a problem very elegantly. Let's start. The first piece, we are going to start with the great mathematician Gauss, and it's a story about his childhood, perhaps when Gauss was in 4th or 6th grade. And this story has many versions, and it's retold and told in many ways. And I'm sure you've heard this story, but it does bear retelling. So I'm going to tell you this story again. So the story goes that Gauss had a teacher who one day came to class and he didn't really feel like teaching. So he thought that he would keep the students busy by giving them a very difficult problem, and instead of teaching, he can relax or maybe do his other work. So he went on the board and he wrote the following problem. He wrote 1 plus 2 plus 3 plus 4 plus ... plus 97 plus 98 plus 99 plus 100 equals. All right. So he told his students to sum up all the numbers from 1 to 100. And the legend says that Gauss was a backbencher, and he rose from his bench and he showed his notebook to the teacher, in which all that was written was the answer. And now there are many versions of this story. Some people say that Gauss was scolded for trying to disturb the class and so on and so forth, but nevertheless, whatever happened, in the end, the teacher had to ask Gauss, how did he do the problem so quickly? Because indeed, Gauss was correct. And Gauss told his teacher, oh, that's a very simple problem. See, what I didn't do was add 1 to 2 to 3, but I added 1 to 100. And the answer that I got was 101. And then I added 2 to 99, and the answer that I got was 101. And then I added 3 to 98, and the answer I got was 101. And then I added 4 to 97, and the answer I got was 101. And I realized that if I add these numbers that way, every time this number will increase by 1 and that number will decrease by 1. So their sum will remain 101. And he was smart enough to realize that there are going to be 50 pairs like that. So the answer was simply 50 times 101. And he was clever enough to do this in his head. And so he had solved this problem very elegantly. This is a beautiful story of a genius. And this is the first story that I can remember that got me hooked to mathematics. When I saw this the first time, when I saw this trick the first time, I said to myself, wow, mathematics can be beautiful. So let's look at this sum and see if we can come up with another explanation of how Gauss summed this up. So maybe a better thing to do is to just generalize this a little bit and say we want to add up numbers, but not to 100, but let's say to n, all right? And so what we can do is we can say this is the sum. So an equivalent way of looking at Gauss's idea would be to write down this sum once again, but this time backwards. So we can write n minus 1, n minus 2, and the last number would be 1. And now we add these sums, but we do them column-wise. So this would be n plus 1. 2 plus n minus 1 would be n plus 1. And you realize that you would just get n plus 1 because the number above increases by 1 and the number below decreases by 1. So their sum is going to remain n plus 1. And so you can easily write this. Okay? And this is repeated addition is just multiplication. So this is n times n plus 1. But this is twice the sum because we added 2 of these series. All right? So that means if we want to calculate the actual sum, we'll have to divide this quantity by 2. All right? And that is, let's give the credit to Gauss. Even though it may have been known to other mathematicians, let's say this is Gauss's beautiful formula. Okay, so let's look at Gauss's formula, if that's what you want to call it, and let's try to see a visual interpretation of this. Now, visual proofs are not really considered formal proofs by mathematicians, but they are extremely useful in helping us understand what is going on, why something is true, why it may be true. So here's a very nice visual way of seeing Gauss's proof. What you can do is you can make a little square, okay, a 1 by 1 square, all right, and its area is 1. And then you can make a 1 by 2 square, and its area, so this is 1 and this height is 2. And then you can make a 1 by 3 square. All right, so this width is always 1. This width is always 1. All right, and this has height 3. And then you can make another one which has height 4. And pardon my drawing, it isn't the most beautiful thing in the world, but hopefully it will convey the point. Right? So let's say this has height n. Okay? All right? So the sum 1 plus 2 plus 3 up to n is actually summing up the area of these bars. Okay? And what we can do is we can enclose this whole thing into a square. Okay? And this square is going to have width n, and it's also going to have height n, right? And now what we can do is we can draw a line we can draw this diagonal, and this diagonal, if it was done properly, will go something like this. And now we can look at the shaded white area. And the first we notice that we have this part of the area, which is actually half of the area of the entire square. So the square has area n squared, so half of that would be n squared over 2. But when we do that, we have left out these little half squares. We get 1/2 for each one of the bars. And since there are n bars, we will get n of them. Each one of them will have an area of 1/2, and this is the same quantity as that because you can write it like that. Okay, so that's a very nice visual way of seeing Gauss's formula, and it does give us some insight or intuition. Okay, let's look at another visual way of seeing the previous formula. So here what we have is we have placed one blue ball, then 2, then 3, then 4, then 5, then 6, then 7. So the number of blue balls, and you have to use your imagination. We have 1 here, 2, 3, and you can think of these as n balls in the last row we have placed, and the number of red balls is actually n plus 1. Okay, 1 more than the number of blue balls in the last row. And what we do is, in this picture, we take any blue ball, let's say this one, right? And this naturally leads us to 2 red balls. Okay, so this one blue ball leads us to these 2 red balls. We can take another one, say for example, I can take, let's say, this one, and this leads me to this red ball and this red ball. Okay, so, right? And what you can do is you can convince yourself that if you take any blue ball, that would lead you to 2 red balls, and if you take any 2 red balls, that will lead you back to that blue ball. Now, what that means is that the number of blue balls is equal to the number of pairs of red balls. Okay, every pair of red ball gives me a blue ball, and every blue ball gives me a pair of red balls. So these 2 numbers must be the same. And what we do is we realize that the number of blue balls is 1 plus 2 plus 3 plus up to n, in this case 7. And the number of pairs of red balls, this is equal to the number of pairs of red balls. Now here, what you can do is you can ask a combinatorist, how many pairs of red balls can be made if I have n plus 1 red balls? And they would tell you that it's n plus 1, choose 2, which is n plus 1 times n over 2. Okay, all right. If you didn't know that, then we already know this because of Gauss. Gauss summed this up for us. This was n times n plus 1 over 2. So this is Gauss. All right, let's write his name. Okay, all right. Although he did it in his childhood, therefore we are giving him credit. So Gauss told us this. So this means we can get a theorem. We can say that the number of pairs of red balls, when you have n plus 1 red balls, must be equal to this quantity. So if you don't know how many pairs of red balls are there, you learn what they are by looking at Gauss's formula. If you knew that the number of red balls is actually n plus 1, choose 2, you get a different way of looking at Gauss's formula. You get a different proof. Okay, there is so much that you can read in this visual diagram. So if you see this one ball at the top corresponds to this pair, the pair which is farthest away. So there is one pair where the difference, if I number these balls 1, 2, 3, 4, 5, 6, 7, 8. So the number of pairs where the difference between the ball numbers is n is 1. Okay, the number of pairs where the difference is n minus 1 is 2. The number of pairs where the difference is n minus 2 is 3. And the number of pairs, and so on, and the number of pairs where the difference is exactly 1, there are n of them, all right? And therefore, they must be equal to the number of pairs of red balls. So 1 plus 2 plus 3 up to n must be equal to n times n plus 1 over 2, which is also equal to n plus 1 choose 2. You can also look at these balls, these blue balls, and count them in another way. So let's do that. So what if I look at them on this arm, right? These are all the blue balls that correspond to the pairs which have 1 in them. How many are there? N of them. These are all the pairs that correspond to where the smallest number is 2. How many of them are there? N minus 1 of them. And so on. And finally, these are all the pairs in which the smallest number is n, and there is just 1 of them. So once again, this is 1 plus 2 plus 3 up to n. All right, and that must be equal to the number of pairs of red balls. You could also read it in this direction, and you get information. So this little visual picture has a lot of information, and by staring at these visual proofs and visual diagrams, you can actually learn a lot. I want to look at one more way of seeing this formula by Gauss, and and this time this is inspired by graph theory. So this is how maybe a graph theorist would try to understand this. Okay, so let's make n plus 1 circles. Okay, so 1, 2, 3, 4, 5, 6, 7, that's good enough. So in this case, n equals 6, all right? And let's draw an arrow, okay? So these are n plus 1 circles. So let's call this number 1, 2, 3, 4, 5, 6, and 7, okay? Or in other words, this is n plus 1. And let's draw all the possible arrows that can go forward from one circle to another. So from 1, we draw these arrows. Okay. And this becomes pretty messy pretty soon, but let's be patient and do that. Okay, and then we draw all the arrows that go forward from 2, and let's go this way to reduce the clutter. Okay, all right, and then from 3, so we have no choice, but we'll have to cross edges, and it becomes a bit full of clutter, but nevertheless, we do that. 4, 5, 4, 6, and 4, 7, 5, 6, and 5, 7, and the last 6, 7 is nice. Okay, all right, and now let's ask ourselves how many arrows will be going out of 1, and the answer is pretty simple. It has n things in front of it, so there must be n arrows going out of 1. From 2, there are n minus 1 things in front of it, so there must be n minus 1 arrows going out. Okay. From 3, there must be n minus 3 arrows going out, and from 6, there'd be 1 arrow going out, and from 7, there wouldn't be any arrows going out since nothing comes after that. All right. So this means that the total number of arrows is 1 plus 2 plus 3 plus up to n. Okay. And now we make the observation that if you take any pair of these circles, there would be an arrow coming from the smaller one to a larger one. So this must be equal to the number of pairs of circles that we can form. We have n plus 1 circles, and how many pairs of circles we can form? Well, a combinatorist would tell you that it is n plus 1 choose 2, and its formula is n times n plus 1 over 2. And once again, we conclude the same thing. You could also see the same thing by arguing how many arrows are coming in to a circle rather than going out. you would get exactly the same information. So another nice, visual, beautiful way of seeing the same thing. This little gem has all the ingredients that make a great mathematical theorem. It is inevitable. It comes up in so many contexts that somebody had to discover it. It is economical. It changes a complicated sum into a compact form. And it is also unexpected. Most mathematicians won't find it unexpected, and I don't, because I've known this for decades. But the first time I heard this argument, the first time I heard that all numbers from 1 to 100 could be added like this, that was a moment of awe. That was unexpected for me at that time. Of course, if something is unexpected and you see it your entire life, then it seems ordinary. But this theorem is beautiful. The second theorem that we are going to look at is also one of the most widely known theorems in mathematics, the Pythagorean theorem. The second theorem that we are going to look at is also one of the widely known theorems in mathematics, the Pythagorean theorem. So now we move on to Pythagoras. Okay, and everybody has studied this in their elementary school or somewhere in their lives, and this theorem has to do with triangles. So we take a triangle in which we have one right angle, and the side that is opposite to the right angle is called the hypotenuse, right? And typically we label it C, and the two other sides are called the legs. And once you label them this way, then the famous celebrated Pythagoras' theorem says that there is a relationship between these three quantities, that the square of the hypotenuse is the sum of the square of the legs. Okay, so actually, since this formula is symmetric in A and B, we don't need to name these things differently. So, you know, we would just call them legs. We just need to know that hypotenuse is opposite to the right angle in the triangle. Now, there are hundreds of proofs of this theorem. This theorem is also inevitable. And this relationship being so simple, and so therefore it is an economical theorem in some sense, it has economy. And this third thing is, it is unexpected. We only think it's obvious because we have been told this all our lives, because we have known this all our lives. The fact that these relationships are so simple, the first time it must have been observed must have been unexpected. This is perhaps the most widely used theorem in mathematics, because every time you want to compute distances, you have to fall back to the Pythagorean theorem. So let's look at a proof of this, and it's a very visual proof, and this is what I call the two-cake proof. The two-cake proof. Okay. And this proof is folklore. It does not appear in Euclid's Elements. A bit of history that the Pythagorean theorem was most definitely known to people before Pythagoras. And it actually never appears in the writings of Pythagoras. The first proof is in Euclid's Elements. Nevertheless, the name has stuck, and so we're going to use that. So this proof, a two-cake proof, what we do is we make two cakes, right? Here's our first cake. It's vanilla, all right? And it's going to be a square cake like this, and you will have to bear with my with my drawings, which aren't very good, but nevertheless I'll try my best. So the cake size is A plus B. So one side has length, so this length is A plus B, and this length is also A plus B. Height is also A plus B. And now what we do is we connect these points, right? And we get 4 triangles, right? So this is B, this is A, this is B, this is A, this is B, this is A. So we get these 4 triangles. And since this is a right angle, here we must have C. Since this is a right angle, here we must have the length of the hypotenuse C also here and also here, right? So we have these 4 triangles. And what we observe is that this angle must be a 90-degree angle, because the sum of these 3 angles is 180, and we have taken out these 2 angles from it. So what must be left over is 180 minus 90. All right. So this inside is a bona fide square. All the angles are 90 degrees and all the sides are C. And what we do with this cake is we are going to eat the triangles. So let's eat the triangles. And so that's our cake number 1. Now let's make our cake number 2. Okay, and I'll try to make it as equal to this as possible. And this cake is also going to have width A plus B and height A plus B. Okay, all right. But we are going to label it slightly differently. So this is A, this is B, this is A, this is B, okay, and this is A, this is B, and this is B, this is A, okay. And now we are going to again eat 4 triangles, but this time in a different way. So I will draw this and I will eat this triangle, I will eat this triangle. So this length would be C. Okay. Another triangle that I would eat is this one. So this length is C. And another triangle that I would eat is this one. Okay. So this length is C. This length is A. This is A. This is also A. Okay. So I started with the same size cakes and I ate 4 triangles from here and I ate 4 triangles from there. They were exactly the same triangles. So therefore, the leftover area here must be equal to the leftover area here. But what's the leftover area here? That's C squared. And what's the leftover area here? Well, that's A squared. That's the little cake, and B squared. That's the slightly bigger cake. This cake actually falls apart into 2 cakes. One of size A by A, so it has area A squared, and another of size B by B, so it has area B squared. Since I started with the same size cakes and I ate the same amount, therefore the leftover must be equal, and therefore C squared must be equal to A squared plus B squared. Adorable, right? And what you would notice in this, and you must have noticed in the previous proofs also, is what we're doing is we are calculating the same quantity twice. So in this case, it's the leftover area of the cakes. We are calculating that in 2 ways, And since we are calculating the same quantity twice, therefore those two numbers must agree. And that means we have an equation. And an equation is information. This is a recurring theme in mathematics. Compute the same quantity in two different ways. And that gives you an equation. An equation is information. Let me show you another proof of this, which I call the one cake proof. Okay? So the one cake proof, what we do is we do not look at the second cake, we just look at the first cake. All right? So what we can do is we can say that the total area of the cake is a plus b whole square. Right? It's a plus b by a plus b cake, and that must be equal to the leftover, which is c squared, plus what we ate. So that is 4 triangles, and if you remember your basic geometry, the area of a triangle is half base times altitude, so this would be half AB. Okay, so on this side you get c squared plus 2ab, and of course you know how to do the algebra here. So this is a squared plus 2b plus 2ab plus b squared. And now what you can do is you can cancel the 2ab to get the Pythagorean theorem, a squared plus b squared equals c squared. So you can do the same proof with just one cake, but you have to do the algebra. Now, when you are writing down a plus b whole squared equals a squared plus 2ab plus b squared, that's what the algebra is in the red cake. See, a plus b whole squared is equal to a squared plus b squared plus 2 rectangles of length a times b by a, and the other one is a by b rectangle. So that algebra is there. And when you're actually cancelling the 2ab, that's when you're eating the cake, right? So you could do it with one cake and algebra, but I like to do it with 2 cakes and no algebra, because that way I get to eat more cake. A beautiful theorem. An extremely useful theorem, an inevitable result. Okay, so let's now go to our third topic. Okay, so for our third piece, we're going to look at something that is not very well known, or at least it's not taught in many schools. And this time our hero is a Greek, and his name is Aristarchus of Samos. Right? And this guy, 2000 years ago, estimated the distance to the sun. Actually, he also estimated fairly accurately the distance to the moon, actually very accurately. And using that knowledge, he actually measured the distance to the sun. And it's just a beautiful piece of mathematics, very simple, very elegant. And he didn't have too much technology at that time. So let's see his method, and then we will talk a little more about it. But we're going to use some technology. So the problem that Aristarchus was tackling was, given that we know the distance to the moon, okay, estimate or calculate the distance to the sun. Okay, and how he actually calculated the distance to the moon is another beautiful story, and I hope you would go and read about it, but we would just stick to this. So let's use technology and see his method. So what we're going to do is, that looks good. Oops. I'm not very good at technology, but nevertheless we have a near circle here, which is good enough. And what we're doing here is we're trying to draw the Earth-Moon system. So at the center there should be Earth. Okay, let's label it E. All right, and let's put the moon right here. Okay, the moon is a lot smaller, but I'm going to just draw it a little bit bigger. Just use your imagination. All right, or maybe I can draw the Earth a little bigger. All right, so that's the Earth-Moon system. And what we do is we ask ourselves, when do we see a half moon? And here is when you would see a half moon. The sun, when it makes a 90-degree angle with the moon. Okay, so this is the sun. Now in reality the sun is very far away, so this picture is sort of an exaggeration bringing the sun down so we would be able to see what happens. So let's see, when the sun is over here, the light of the sun will shine the top part of the moon, okay, and the bottom part of the moon would be dark, okay. So if we were to look at this picture from the Earth, it would look like a half moon. Okay, this would be the light part shining because the sunlight is shining it, and this would be the dark part because the sunlight is not shining it. And this is where we will have the half moon. Okay, so let's use technology again and now do something that Aristoteles did. Let's draw a line from the sun to the center of the Earth, all right, and keep going and stop when it hits the circle again. And let's ask ourselves, the moon is going round the Earth, right? And what would happen when the moon is at this point? And what would happen if the moon is at this point? All right, so let's argue it out. When the moon is at this point, from the light of the sun will light up this side. Okay, so this side would be bright and this side would be dark. Okay, but see, the bright side is not visible from the Earth. All right, so if we look at the situation here, right, the moon would be completely dark. Okay, it's what we can call a no moon. Okay, you would not see the moon, it would be all dark. All right, okay, let's see what happens if we look at what happens at this point when this line crosses this circle. Now, you might think that the sunlight would not reach there. And that's true. When an eclipse happens, that's exactly what happens. The Earth comes between the moon and the sun, but the Earth-Moon system is tilted, slightly tilted. So most of the time we don't get an eclipse. So the light actually, so it's tilted like this, the light actually can pass underneath the Earth or over the Earth, and therefore it does reach here. And what we have here is this light, it will shine this part, and this part would be dark. Okay, so if we observe what's happening here, what we would see is a full moon. Okay, so this would be a full moon. Okay. Now, what Aristarchus does is he draws a perpendicular line on this circle. And if you think about this, this is halfway. This point is halfway. And the beautiful observation is that the half moon happens earlier than halfway. The half moon happens earlier than halfway. And why is that? The reason is because sun is at a finite distance. Now, if the sun were closer, then you can think about this and you would realize that it would happen even earlier. If the sun is far away, then this half moon will happen near the half point. So what we have to do is, what we can do is, we want to measure this angle. Let's call it alpha. If we measure this angle and we know the distance to the moon, then of course we know enough trigonometry, and Aristarchus did know enough trigonometry to estimate or calculate the distance to the sun. So all he needs to know is this angle. Now, elementary geometry will tell you that this angle is the same as this angle. And that I leave as an exercise for you, right? So this angle is the same as this angle. And what is nice is we know that the moon goes round the sun in 1 lunar month. And the speed of the moon is more or less constant, right? It does vary a little bit, but that's a finer point. So the angular velocity of the moon is constant, and therefore angle is proportional to time. So all he had to do was to figure out how earlier the half moon happens before the half time, right? So if you calculate, this is 1 lunar month, this is half a lunar month, and this is quarter of a lunar month. So how much earlier does the moon become a half moon? If he knows that, then he can estimate the distance to the sun. Beautiful. And he was able, I think he wasn't able to exactly find out how earlier the half moon happens because he didn't have very good clocks and he had to make his observations at night. Nevertheless, he estimated that the sun is pretty far away, very far away, and he also realized that the sun must be at least 20 times larger than the Earth in terms of radius. That means 8,000 times larger than the Earth in terms of volume. So from there, he actually argued that the Earth must go around the sun, because he knew that the moon goes around the Earth and moon is a smaller object. And since the Earth is very small compared to the sun, so it made sense for him to just say that the Earth should go around the sun. And he was the first person to come up with the heliocentric model of the universe. And most of you thought it was Copernicus. No, it was Aristarchus. And Copernicus in his book acknowledges Aristarchus as being the first one to propose this model. But this is an absolute triumph of simple mathematics. Just high school level or even elementary school or middle school level geometry and just simple logic that tells us how can we estimate the distance to the sun. And then from there, Aristarchus going on and coming up with the right model of the solar system, the heliocentric model. The reason Aristarchus went out of fashion was Ptolemy came up with the geocentric model. And when people asked Aristarchus to explain his model, and they asked him that why don't we see parallax in the stars? He said they're very far away, they're extremely far away. And that argument didn't go down well with the Greeks, so they stuck with Ptolemy. And after that, there's a beautiful story of how we once again went back to the heliocentric model. But this is an absolutely fabulous piece of mathematics, and simple and consequential. Okay, so I hope you have enjoyed these 3 pieces which I have selected for the sample lecture. The course itself would be a little more involved than this, and we would look at not only the ancient classics but also some modern stuff. So I hope you enjoyed this time, and I'll see you in the lecture. Thank you.